Welcome everyone. In this video lecture, we will think about the delay time estimation in a CMOS inverter and its definitions. Okay. So first of all, we have already draw the CMOS inverter circuit having NMOS M1 and M2 PMOS transistor. The gate is connected to the input and we are taking output across the drain in. So fundamental circuit. So the corresponding input and output waveform we have to draw for a traditional CMOS inverter circuit. So I have already draw the input which is given to the inverter circuit. This is the input. So this black line, we can say this black line or this line is the idealized step input. Okay, idealized step input. Step input is there. Okay, and this one is, we can say, the practical kind of input we are giving. Means it is started from VOL, it will cross at V50 and rising input and then falling input like this. Okay, ideal one. And this one we can say the green one, we can say the practical input, we can say practical input, we can say. Okay, now this one is the input. It will start from VOL. Okay, it will go up to maximum VOH. A step input is the ideal one, and this one is the practical one. So we have to draw the corresponding output waveform. So we are very familiar that when the input is low, output will be high. So when output will be high, when input is low, for this to this point, say this point is say T naught, T naught point. Okay, from 0 to T naught. Okay, input is somehow low. Okay, so output will be a high value VOH. So what we can do, we are doing the VOH. Okay, then after out input is high, so output will be low. So now it will go down or it will decrease. Okay, so how it will decrease? For this purpose, once again, one more thing. Say this point is our VOL. So practical output will be like this. It is it will start decreasing. It will come. Okay, go like this. Okay, means ideally it will go. It will decrease like this. Okay, when input is low, output is high. Okay, this point. Okay, try to understand it. And then input is high, output is going to low value. It will come here. Okay, and one more line I am just drawing. This point is, and then after it will, and say this value is our VOH value. And then after it will go from this point, it will close like this. Okay, okay, means this one is the output waveform. Clear? This one is the output waveform. So this point is, say I am saying T naught, and this point where it cuts the V50 line is our some point, say that is our T1, and this point, okay, say T2, and this point where it cut the this V50 line is our T3. So this time span is called our tau PHL, power propagation delay from high to low, when the output is VOH and it will come to the 50%. Okay, and this one is called our tau p low to high. Okay, clear. So this one is the definition, means first input is low, output is high. Okay, input is low, output is high, it is at VOH. Then after it start decreasing. Okay, and it go up to VOA, and then again when the input is become low, it start increasing. Okay, and it cut at 50%, it will go. So this time is our tau PLH, low to high propagation delay, from low to high. So definition, what we definition we can say, the propagation delay, we can write here, we can write the propagation delay. Okay, the propagation delay or propagation delay time, that is our tau PHL and tau PLH. High to low and low to high determine determine the input to output signal delay during the high to low and low to high transition of the output. Okay, respectively, we can say respectively. Okay, means the propagation delay time tau p determine the input and output signal delay. Okay, during the high to low, that is our tau phl, high to low, high to low. Okay, that is our tau phl, and low to high, low to high, that is our tau plh in the transition of the output. So this one is our tau phl, and this one is, okay, this time. And ideally we can say the tau phl, so we can simply write that. Okay, the hence we can write tau phl is nothing but simply t1 minus t naught. Okay, and this one tau p low to high, tau p low to high is our t3 minus t2. Okay, t3 minus t2 time is this one, and t1 minus t naught is our tau phl. Okay, this one is one definition that we have already covered. Okay, this one is our one definition. Then after, what we can say, the other definition of the propagation delay. Okay, the other definition of a propagation delay, we can say the tau phl, the tau phl. Okay, the tau phl, tau phl is the time. Okay, tau phl is the time delay. Okay, this one time delay is the time delay between, okay, between how much, between the V50% of the rising input voltage. Okay, I will show you this one. V 50% of the rising input voltage, that is our T naught, and the V 50% transition of the V50% transition of the falling output voltage. Okay, means tau phl, this distance, this and falling one. Okay, at V50%. So this one is called a tau phl, time delay between the V50% of the rising input, okay, and the V50% transition of the falling input. So this one is our, this basically tau phl. Similarly, we can write the definition for this one. Tau PLH is the time delay between the V50% of the falling input, falling input voltage. Okay, V50% of the falling input voltage, where it is falling input voltage, this one. Okay, falling input voltage and the V50 V50% transition of the rising input voltage. Okay, very similar to that, but here in tau plh we have to say the time delay between the V50% of the falling input, okay, and V50% of the rising input voltage. Okay, so these two are the, we can say the definition, and mathematically also we can write V50% is what? V50% is nothing but simply VOL, input law, plus, okay, 1 by 2 times of VOH minus VOL. Okay, simply V50% VOL plus 1 by 2 VOH minus VOL. Okay, so if we solve, it will come simply 1 by 2 times of VOH plus VOL, VOH plus VOL. Okay, clear this one? Now the propagation delay tau p. Now propagation delay, the average propagation delay is called as tau p hl plus tau p lh by 2. So this is one definition for the propagation delay and all. Okay, very fundamental definition is there. Okay, clear this thing? Okay, so in addition to that, one more definition we can say, that is also very simple. So that I want to show in terms of V 10% and we are 50%. We can also, okay, for this thing I'm just making one that. For example, this one is our output curve, and we are just making the output waveform from VOH. Okay, and we are going like this, and the output is increasing like this. Okay, so this one is our say VOH. Okay, and one line I have made. Okay, I am saying this is a V 90%, and one line I am saying this one is our V 10%, and one more line, that is our VOL. Okay, so VOL. Okay, this point is VOL. So one more definition we can say in terms of if 90% and it is cut, and it is cut here. Okay, so if I am saying this one is TA point, TB point, okay, and this point is say TC point and TD point, in terms of V90 percent percentage voltage, in terms of 90%, 10%. Okay, so this end is called a T fall. Okay, and this one T rise. Okay, T fall, T rise. So T fall simply our we can say TB minus TA, and T rise equals to TD minus TC. Okay, or we can make it capital D. TC minus TD. Okay, so this one is one more definition in terms of percent. It may be 20%, 40%. So you can define like this. Okay, and the value of V 10%, we can simply write it VOL plus 0.1 of VOH minus VOL, and V 90% is simply VOL plus 0.9 times of VOH. I am just writing. Okay, so this is one other example means definition in terms of, okay, means other definition, other delay definition can be done by using 20%, 80%, or 30%, 70%, anything. Okay, so this one is the just definition for the delay time estimation. So we will derive the delay time for the CMOS inverter in other video. So thank you for watching this video. So this is all about the some fundamental of the delay time estimation in a CMOS inverter. So thank you for watching this video. Thank you.